In the previous lecture, we discussed about the Reynolds transport theorem for infinitesimal control volume by considering the extensive quantity as linear momentum. Okay, and there we derived this equation. Okay, so we derived that rho dx dy dz, the material derivative of the velocity, equals the summation over all the external forces on that control volume, on that infinitesimal control volume. Correct? Okay. Then I told you that the derivation is still incomplete, since we have to put the forces due to shear stresses, the normal stresses, and the body forces. Okay, and to motivate you for the upcoming lectures, I told that if you put these things inside this equation, what you will get is the most popular equation in fluid mechanics, which is Navier Stokes equation. Now, before going into that derivation, let's first understand various things that will be helpful during the derivation of the Navier-Stokes equations. Okay. Let's first consider the shear and normal stresses. To understand them, let's consider a cube and the coordinate axes x, y, and z. Okay. Now, if I tell you that, let's say the fluid is static, then what is the normal stress on this static fluid? What would that be? So that will be nothing but the pressure, right? So pressure acting from this side, the pressure acting from this side, so on all the faces perpendicular to the faces. Okay, so like this, like this, like this, and like that. Okay, all right. So you know that we can find the normal stress on the static fluid. Okay, so that is, let's say the magnitude is the pressure P. Okay, now if I ask you what is the shear stress on this fluid element for a static fluid, what will that be? So since there is no relative velocity between the layers of the fluid, so I will say that the shear stress is 0. Okay, all right. So now let's say I tell you that, now assume that the fluid is moving so let's say this top plate is moving with a constant velocity u. Okay, and let's say the relative velocity between the layers is u, so if this is u, this will be 0. So the, let's say this plate is held with the ground stationary. Okay, so this will have 0 velocity and this will have u velocity. So if I give you this problem that let's say the relative velocity between the fluid layers is, let's say, u, and let's say this u is constant and directed along x-axis. Okay, and I ask you now, what is the normal stress So let's say let me just first write it, fluid moving. Let's say the first condition is it is moving with constant velocity. The one layer, so the relative velocity between layers is constant and it's just u along x-axis. Okay, so if I give you this question, then what, according to your current knowledge, you may say that the normal stress is again P and the shear stress is, so from the Newton's law of viscosity, you will say that I know from the Newton's law of viscosity it will be mu del u by del y. Okay, so this is correct. Now let's say if I ask you, now instead of a constant velocity u, we know that the velocity, let's say the relative velocity is some v, which is ui hat plus vj hat plus wk hat, and also it is not constant. Okay, so u, where u can be a function of x, y and z, v can be a function of x, y, z, and w can be a function of x, y, z, then what can you say about the normal stresses and the shear stresses? So you may say that again the normal stress is pressure P and shear stress from Newton's law of viscosity will be mu del u by del y, or maybe you can guess that, you may guess it like that. So you may guess that it would be something, let's say del u by del y plus del v by something plus del w by something. Okay, but you are not in a state to exactly predict what will be this answer. Okay, so what is the reason here? Firstly, let me tell you that the normal stress for this moving fluid with this condition is not only P, but there will be some contribution also. And for the shear stress, you need to know, what you need to know is Newton's law of viscosity in 3D. Okay, we'll come to this later. Let's first understand whether the stresses are scalar or vectors, or whether they are something else. So let me just rub this, since this was only for one condition. Okay, so let's consider this case when the relative velocity between the layers was constant and directed along x-axis. So then we said that the normal stress will be P. So the direction of this normal stress was like this. So this was P directed like this, pressure directed like this, pressure directed like this, and also on the other two faces like this and like this. Okay, so this is perpendicular to the faces. Okay, let's just rub this for clarity. Okay, now if I ask you whether this normal stress is scalar, you will say no. Why? Because it has a direction. Alright, so then now whether it is a vector, you might say yes, since it has a magnitude as well as direction. But let me tell you this, that to get the direction of this normal stress, what you needed was the area or the area vector. Okay, so if I had given you an area dA vector, you will say that the pressure is always anti-parallel to dA vector and will be P, and its direction will be minus dA hat, or let's say minus n hat, where n hat is the normal vector of the area vector. Okay, all right. So from this I can argue that to get direction of stress, what I need to know is the area vector and the magnitude. Okay, direction of stress and the value. Let's just only focus on the direction. So we need to get the direction of normal stress. To get the direction of normal stress, we need to know the area vector. Okay, next let's focus on the direction of shear stress. Okay, so let's just rub this P and focus on this area. Okay, now consider this condition where velocity is given by u hat plus vj hat plus wk hat, and it is also a function, the magnitudes u, v and w are also the function of x, y, z and also time. Okay, so in that case it has been seen that this shear stress on any face has three components: one along y, one along z and one along x. Okay, now similarly, if I consider this surface, the shear stress there will be directed along x, will be directed along y and will be directed along z. Okay, oh actually I should say the stress, not the shear stress, because these components will be the part of the shear stress and this will be the normal stress. So let's call that it has been seen that, or I should better call it that the stress, it is seen that on a surface it has three components directed like this, like this, like this, and for this surface the stress components are directed like this. Okay, and these components may or may not be same. So for this also we need area vector. Now let's say I ask you to write the stress in terms of I hat, j hat and k hat. Will you be able to do that? No, because you will ask me that I don't know the area vector, so I cannot write this in terms of I hat, j hat, k hat. Thus to denote a stress we need two things or two subscripts, with one telling me the direction of that stress and the other telling me the direction of area vector. Okay, and this stress is usually denoted like with this Greek letter tau and subscripts ij. So this I and this j So I tells me the direction of normal area vector and J tells me the direction of stress. In some books, to differentiate the notation for the shear stress and the normal stress, they use tau ij and sigma ii, where this tau tells you that you are talking about shear stress, and with the sigma telling you about that you are talking about normal stress. Okay. However, in some books, people use tau to emphasize the stress due to viscosity of the fluid, and did not give the notation sigma. Okay. You can follow any of the notations as far as your notations are consistent. Okay. Now let me tell you that the things or the physical quantities that require two subscripts, or let's say the subscripts I is going from 1 to 3 and j is going from 1 to 3, then in total I'll have 9 components of the stress, or 9 components of this quantity. So these type of quantities are called tensors. Okay, so basically stress is nothing but a tensor. Many people refer vectors, many people refer scalar as zeroth order tensor, vector as first order tensor, and similarly you have second order tensor, third order tensor, and so on. But let's for time being stick to the concept that if I am calling stress tensor, you should know that I am inherently calling a second order tensor. Okay, that is, it has 9 components for its complete description. Okay. Since this concept of tensors is new, let's try to denote stress tensor for all the surfaces of this cube. Okay. Before that, let me just first write the convention that we are going to follow. So I'm going to denote my total stress tensor as sigma ij. Okay, and shear stress tensor as tau ij. So this shear stress tensor will originate because of the motion of the layers of the fluid. Okay, all right. So then I can write this sigma ij as sigma xx, sigma xy, sigma xz, sigma yx, sigma yy, sigma yz, sigma zx, sigma zy, sigma zz. Okay, where this I is the direction of normal area vector, and j, let me just mark it with some other color. So this j is the direction of stress tensor. Okay, now let's try to understand this the direction of this stress tensor by considering the different faces of this cube. So let's consider first this face of the cube. So what will be the stress tensor on this cube? What will be the component of the stress tensor on this cube? Let me just use a different color. Okay, so now we know that the area vector is pointing in the positive x-axis, and if it is acting in the positive x direction, so then I can write the stress tensor here as sigma xx, here as sigma yx, and here as sigma zx, sigma xz. Okay, all right. Similarly, if I consider this face has normal vector in the positive y direction. So the stress tensor for this surface will be given as, so this will be given as sigma yy, this will be given as sigma yx, and this will be given as sigma yz. Okay, oh sorry, this is wrong. So since the normal, since I want to find along y-axis, y should be outside, and it is on the with the area vector which is pointing the positive x direction, so this will be sigma xy. Now let's say if I want the how pressure is acting, so on this face, let's say how pressure will be acting, it will be acting in this direction. Now you can see, and also what will be tau xx, so tau xx will be in the direction of sigma xx. Okay, so now if I ask you how can I write sigma xx in terms of tau xx and p, what will you say? I'll say, let me just write it with some other color. So I will say sigma xx is equal to minus p plus tau xx, because p is acting opposite to sigma xx and tau xx is acting in the direction of sigma xx. Okay, and similarly I can write sigma yy as minus p plus tau yy, sigma zz as minus p plus tau zz. Okay, and since this p will be acting along sigma xx, sigma yy, sigma zz only, the other terms like xy, yx, xz, zx, yz, zy, they'll not contain p, and they will just contain tau. So I can just write like this. Okay, so in that case, if this is the case, then I can write my stress tensor, total stress tensor sigma ij, which is sigma x, sigma xx, sigma xy, sigma xz, sigma yx, sigma yy, sigma yz, sigma zx, sigma zy, sigma zz. I can write this as, since sigma xx is minus p plus tau xx, sigma yy is minus p plus tau yy, and sigma zz is minus p plus tau zz, and I can write tau xy as sigma xy as tau xy, sigma xz as tau xz. Similarly, I can write this as tau yx, I can write this as tau yz, I can write this as tau zx, I can write this as tau zy. Okay, so this is my total stress tensor in terms of tau and p. Okay, so now let's say if I ask you what is the force, so if I ask you what is the total force along x-axis, then what will you say? So then, since I know, so I will take the stress tensor which is directed along x-axis times I have to still write a subscript here, times the area. So this will give me the force because of the component of that stress tensor. Okay, and now since with this outer subscript x, I have how many terms? So I have sigma xx, sigma yx, and sigma zx. So there will be these three sigmas that will contribute to the force which is directed along, which will be along x-axis. Okay, so let me just write it like I, and where I is x, y, and z. Okay, so similarly we can find the total force along y-axis or the total force along z-axis using the stress tensor components. Okay, now let's say I give you a question that, so what is the force, what is the force due to stress on a plane whose normal vector is given as n hat is equal to nx I hat plus ny j hat plus nz k hat. So what is your answer? So the answer to this is given by Cauchy's stress relation. Cauchy's stress relation, which states that fx by a, f by a, if I want to find the forces due to the normal stress, I have to just multiply these matrices. Okay, so let's understand this by one example. So let's consider this was our cube. So let's consider I want to find the force on this surface, let's say. So the dA vector of this surface is pointing, so let's say this is the same coordinate axis x, y, z. So then the dA is pointing along positive x-axis. Okay, all right. So then what will be the n vector for, so now I want to find the stress on this plane, on this surface, okay, using the Cauchy stress relation. So what is n vector for this? N vector is I hat only. Okay, so this implies nx is 1, ny is 0, nz is 0. Okay, so let's put it in that formula for the Cauchy's relation. So what I will get is fx by a, fy by a, fz by a equal to 1, 0, 0 times the sigma matrix. Okay, all right. So now I know that, so now from this I can find fx by a, which will be 1 times sigma xx plus 0 times sigma yy, xy plus 0 times sigma, okay, this is sigma yx, sigma zx. So in that case I'll get fx by a equal to sigma xx, and similarly I will find fy by a equal to, so this is my sigma xy, so 1 times sigma xy plus 0 times sigma yy plus 0 times sigma zy, which will give me sigma xy, and similarly fz by a will be sigma xz. Okay, so this was sigma xz, sigma x, sigma yz, and sigma z by sigma zz. Okay, so this is how we can use the Cauchy stress relation to find the force vector, the force due to stress on any plane whose normal vector n hat is given by this. Okay, all right. Now if you have understood the stress tensor, let's come back to our equation, which was rho dx dy dz vxyz equal to summation over f external. Okay, our job is to write this f external in terms of all the forces due to shear stresses, the forces due to normal stresses, and the forces due to body forces. So I think it's the correct time to tell you what a body force is. So body force is nothing but a force that acts on the complete body. So what is the example of this? It's gravitational force, right? The weight of the body is an example of the body force. Okay, so now to write these stresses, what I need is the area vectors. So let's consider this cube in x, y, z axis, and now let's say I am interested in finding the total force along x axis. Okay, so the total force along x axis will be summation sigma ix area and I going from x, y to z. Okay, where this area is the area of the surface. Okay, so if that is the case, then let's say if I have this surface, then now let's say if the total stress tensor at the center of this cube be sigma, okay, then what will be sigma for this plane? This will be given by Taylor series, and similarly sigma on this plane will be given by Taylor series. Okay, so now let's focus on this thing. So total force along x axis, so this should be actually 2 times, because if you see it carefully, this should come twice. Okay, so now we want to find total force along x axis. So let's consider first this surface. Okay, so what will be the component of sigma which will be significant for the force on this plane along x axis? That will be sigma xx plus something which will be found from the Taylor series. Okay, so let's just write this. So let's call it surface. Let's say this is surface 1. So the force on 1 along x axis will be, so this is the total stress force along x axis due to stresses. So let me just first write this, the complete definition of the total force. So the total force along x axis will be 2 times summation I equal to xyz sigma ix, and this sigma x should be at for that particular plane that you are talking about, then area of that plane plus the force due to body forces. Okay, so let's say the body forces db df dfb in the x axis. Okay, now let's consider this area surface, this plane 1. So what will be sigma directed along x axis on this one? That will be given by the Taylor series, that which will be sigma xx plus del by del x sigma xx times, so if this is dx, this will be dx by 2, so times dx by 2. into the area. So what is the area of this? The area will be dy dz. dy dz. Okay. So this will be the force on one along x-axis only because of the stresses plus some. Okay, so since this is only for the body, okay, so we'll write it at the end when we'll consider all the surfaces. Then after that we'll write this term. Okay, all right. So this is for the stress force for one along x-axis. Similarly, let's say if I call this as 2, then for 2 my stress force will be given by sigma xx plus del by del x minus, so this will be minus sigma del by del x sigma xx dx by 2 and multiplied with dy dz. Okay, correct. So let's define, let me define it with some other color. So let's just define this as the total surface force along x-axis. Let's call the total body force along x-axis. So now if you consider all the faces, what you will get is the following. So you will get dfs x equal to sigma xx plus del by del x sigma xx dx by 2 times dy dz minus sigma xx minus del by del x sigma xx dx by 2 times dy dz. So these were my first surface and second surface. The stresses on the first surface and second surface along x-axis, actually the force because of these stresses, plus now if I consider other surfaces which have a normal vector pointing in the y direction, I will get tau, actually not tau but sigma yx plus del by del y tau yx, not tau but sigma yx dy by 2, and the area will be given by dx dz minus sigma yx minus del by del y sigma yx dy by 2 into dx dz. And similarly for the planes which have normal vector along z-axis, I will get this as sigma zx plus del by del z sigma zx dz by 2, and the area will be dx dy minus sigma zx plus, not plus, by del z sigma zx dz by 2 and dx dy. If you notice here, I have also written minus signs. So how will you get those minus signs? This you can get from the Cauchy's relation, because if you consider this surface, this will have n hat in minus j hat direction. Okay, and because now if you put this in your Cauchy's relation, you will get a negative sign in front of this term. Okay, so that's why I'm getting negatives also here. All right, now if I simplify this, some terms will get cancelled out. So this sigma xx gets cancelled out with sigma xx, sigma yx gets cancelled out with sigma yx, sigma zx gets cancelled out with sigma zx, and I'll be left with, so d, the surface force on this volume element to infinite small volume element along x-axis is del by del x sigma xx plus del by del y sigma yx plus del by del z sigma zx times dx dy dz. Okay, and the body force along x-axis, since it is because of the gravity, I can write this as rho gx times dx dy dz. For the time being, we are not assuming whether the gravity is acting along x-axis, y-axis or z-axis. We are not particularly considering the direction of this gravity vector. So let's just assume that my gravity vector, acceleration due to gravity, is gx I hat plus gy j hat plus gz k hat, and later we can say that g is along only k, and we can put gx and gy to be 0. Okay, so for the time being, let's assume acceleration due to gravity like this. Okay, alright, so this is my surface force because of the stresses along x-axis. This is my body force along x-axis. Now similarly, if I consider the forces along y, I'll get del by del y sigma yy plus del by del y. Okay, sorry, this will be del x, del by del x sigma yy plus del by del y sigma xy plus del by del z sigma zy times dx dy dz, and the body force along y will be rho gy dx dy dz, and dfs along z will be del by del x sigma zz plus del by del y sigma, actually there is a correction here, so it should be xy yy, and here it will be sigma xz, this will be sigma yz, and this will be sigma zz times dx dy dz, and similarly the body force along z is rho gz dx dy dz. Okay, so let's club all those forces. So f external vector, since it is on differential element, let's just write it df. So what this will be? This will be dfs along x plus dfb along x I hat plus dfs along y plus dfb, the body force along y j hat plus dfs in z plus dfb in z times k hat. Okay, so what was this term? This term was del by del x sigma xx plus del by del y sigma yx plus del by del z sigma zx times dx dy dz, and since dx dy dz will be common in all the terms, we'll take it, let's say here. Okay, so this was dfsx. Now what is dfbx? Dfbx is rho gx times dx dy dz, which we have already taken here. Now similarly, I can write other terms. So this will be del by del x sigma xy plus del by del y sigma yy plus del by del z sigma zy plus rho g y plus del by del x sigma xz plus del by del y sigma yz plus del by del z sigma zz. Okay, and I had sitting outside. Actually I had is also with this term, so let me just write it with black. I had sitting outside, j hat sitting outside, k hat sitting outside here. Okay, now since we know sigma, since we know the matrix, let me just write it here. So we know sigma ij, which is sigma xx, sigma yy, sigma zz, sigma xy, sigma xz, sigma yx, sigma yz, sigma zx, sigma zy. It is actually minus p plus, I think I will not have much space here, so let me just write it here. So it is minus p plus tau xx minus p plus tau yy minus p plus tau zz, and this will be tau xy, tau xz, tau yx, tau yz, tau zx, tau zy. Okay, so which means that sigma xx is minus p plus tau xx, sigma xy is tau xy, sigma xz is sigma xz, tau xz. So writing all this, what I'll get is, so let me just firstly copy paste this equation so that I don't have to write it again and again. So copy and then paste. So I had this. Okay, now what is my sigma xx? So sigma xx is minus p plus tau xx. Sigma yx is tau yx, sigma zx is tau zx. Similarly, sigma xy is tau xy, sigma yy is minus p plus tau yy, sigma zy is tau zy, and similarly here sigma xz is tau xz, sigma yz is tau yz, and sigma zz is minus p plus tau zz. Okay, so this equation gets simplified to this equation. Okay, now let's further simplify this. So I have df external divided by dx dy dz is equal to, so let me just take the pressure terms separately, the gravity terms separately, and the stress terms separately. So what I'll get is minus del by del x, I had j hat del by del y plus k hat del by del z times p, okay, plus rho gx I had plus gy j hat plus gz k hat, okay, and then the stress terms which are del by del x tau xx plus del by del y tau yx plus del by del z tau zx, all this multiplied with I hat plus del by del y del by del x tau xy plus del by del y tau yy plus del by del z tau zy j hat plus del by del x tau xz plus del by del y tau zy plus del by del yz del by del z tau zz times k hat. Okay, so can you recognize this term? What is this? This is grad vector. Okay, can you recognize this? This is g vector. Okay, so let's just write it. So this will become d, well, let's not write it again and again. So this will be equal to minus grad p plus rho g plus, now let's try to understand what is this term. Okay, so if you think carefully, then I can write this as in terms of the matrix. Alright, since this is not the matrix, I should not write it in terms of the matrix. So this is divergence of tau ij. Okay, and since I had df external, what I had was rho g, actually rho dv by dt. Actually this was not volume, but this was velocity. dv by dt is equal to f external, and this f external was, since it's on an infinitesimal volume, it should be written like df external, and this was multiplied with dx dy dz also. So if I take dx dy dz on the right side, what I'll get is this, but this term in the right, on the right hand side, we just found this to be equal to this thing. Okay, so then we can say that rho by dt is equal to minus grad p plus rho g plus divergence tau ij. Okay, so what does this equation tells me? So the equation that we just got, this tells me that, so this is the total force on the infinitesimal volume element, total force per unit volume on an infinitesimal volume element is equal to the pressure force per unit volume plus the body force per unit volume plus the viscous force per unit volume. Okay, this equation is referred to as Cauchy momentum equation. Okay, now let's focus on the shear stress tensor tau ij. Okay, for incompressible fluids is the following. Okay, so this is my this is my shear stress tensor for incompressible fluid. Okay, what is mu? Mu is the absolute viscosity of the fluid, and the velocity field is ui hat plus vj hat plus wk hat. Okay, this equation I have taken from the book Fluid Mechanics, Fundamentals and Applications by Chingal. Okay, and if you are interested in knowing the derivation of this tau ij, please see the book Transport Phenomena by Bird, Stewart and Lightfoot. Okay, so in section 1.2 you can see the outline of this derivation. Okay, now let's focus on the shear stress tensor. In this we can see that tau xy term, which is mu del u by del y plus del v by del x, and tau yx term, which is also mu del u by del y plus del v by del x. So this is equal to, this term is equal to this term, and also in here this tau zy is equal to tau yz, and also tau zx is equal to 2xz. So this means that our shear stress tensor matrix is a symmetric matrix, right? So this is a symmetric matrix, or we can say that the shear stress tensor is symmetric, or we can call it as symmetric tensor. Okay, so now from this matrix you can understand that, let's say if you had two plates and this plate was moving with some velocity u, which is not constant but a function of x, y, z and t, and there was a fluid in between the two plates, this plate is held stationary, then I have to get all the matrix components to write the force or the shear stress acting on the fluid. Okay, I cannot just simply say that this is mu del u by del y, where my this axis is along y. Alright, so this you should be very much careful about. Okay, alright, let me just sub this. Okay, so now if you have the components of the stress tensor matrix, now I can plug these components in this Cauchy momentum equation to get the most popular equation known as the Navier-Stokes equation. Okay, so let's do it. So let's first write the Cauchy's momentum equations in three orthogonal axes x, y, z. So let me just first write the Cauchy's momentum equation. So Cauchy's momentum equation was rho g vector minus grad p plus divergence of tau ij is equal to rho dv by dt. Okay, now let me just copy paste the results from the book for Cauchy's momentum equation in the three orthogonal axes. So this is the Cauchy's momentum equation in the three orthogonal axes x, y and z. Okay, I have taken this equation, I've taken this image from the book Fluid Mechanics by Frank M. White. Okay, next let's use the stress tensor matrix which was given by this and plug the components tau ij in this Cauchy's momentum equation in three orthogonal axes. Okay, this will be very. So let's plug these components inside this equation and let's see what we get. Now please note that this equation that we just wrote for the shear stress components, this is only true for incompressible Newtonian fluids. Okay, so now since we know that for Newtonian fluids viscosity is constant. Okay, so this equation is true for incompressible and constant viscosity fluid. The fluids whose viscosity does not change as a function of the applied shear stress. Okay, so then if you put, let's say, 2xx in here, and it has a partial derivative del by del x sitting outside, and since your mu is constant, we'll have mu outside of this equation, of this differentiation. Okay, so please keep this in mind while plugging this into this equation. So now let's just copy paste the result from a book. So this is the result that we get after putting the values of tau ij components in Cauchy stress Cauchy momentum equation. Okay, so this is the equation that we get for x, y and z axis. Okay, with this d by dt sitting here as the material derivative. Okay, so you must note that these equations are for incompressible fluid and with constant viscosity mu. Okay, so this equation that we just derived are one of the most popular equations in fluid mechanics, and these are known as Navier-Stokes equation. Okay, these equations, as you can see, are coupled non-linear partial differential equations, and in most of the cases they are not easy to solve. So that's why what we do in fluid mechanics, when we are given a problem and we have to apply this Navier-Stokes equation, what we do usually is that we take a lot of assumptions, a lot of valid assumptions that does not change the physics of the problem, and try to solve the problem. Okay, the vector form of this equation is given as rho dv by dt is equal to minus over grad p plus mu grad square v plus fb, or let's just write it like this, fb. So what's this? This is the pressure force per unit volume. This is the viscous force per unit volume, and this is the body force per unit volume. Okay, and since these equation, let me again explicitly write this, that this is for incompressible fluid and Newtonian fluids. Okay, that is mu is equal to constant for them. So this is our momentum equation for an infinite small volume element considering incompressible fluid and constant viscosity fluid. And if you remember, we had, using the mass conservation, we had continuity equation which gave us del rho by del t plus divergence rho v equal to 0. But now since we are talking about incompressible fluid, del rho by del t will go to 0. Okay, and this rho can be taken outside of the since this is a derivative, so I can take this outside since it is now independent of xyz. So then this will become divergence over v equal to 0. Okay, so let's now summarize what we did to reach the Navier-Stokes equations and to reach the continuity equation. So we started with Reynolds transport theorem for mass by considering extensive quantity as mass and then as linear momentum for infinitesimal control volume. Okay, now from extensive property as by considering mass as the extensive property and conserving mass since we are in the non-relativistic regimes, we derived the continuity equation. So we got continuity equation which was given by this. Okay, then by considering linear momentum as extensive property and using dp by dt is equal to summation over f external and using the stress tensor, we derived the momentum equation or the Navier-Stokes equation for the incompressible fluid. So Navier-Stokes equation, so the shorthand notation is NS. So Navier-Stokes equation that we derived was given by, in the vector form, it was written as rho dv by dt is equal to minus grad p plus mu grad square u grad square v plus body force per unit volume. And we said that this is for incompressible and Newtonian fluids, that is for the ones which have constant viscosity. Okay, so now in a question, if it is given to you that if the fluid is incompressible and Newtonian, that is mu is constant for that fluid, then we can directly write the differential equation for that fluid element as the following. So the first is the continuity equation, divergence v equal to 0, and the second is our Navier-Stokes equations, which is in the vector form given as dv by dt equal to minus over grad p plus mu grad square v plus fp. Okay, so this is our continuity equation and this is our Navier-Stokes equation for incompressible and Newtonian fluid. Okay, and then we can solve the problem and get the detailed information about our fluid, okay, and its properties. Also explicitly write the meaning of these terms. So this term is the pressure force. Let me just write it with some other color. So this term, and this term, they mean the following. So this is the pressure force per unit volume. This is the friction force or the viscous force per unit volume, and this is the body force per unit volume. Okay, so there should be a vector over here as well as over here. Okay, let's also write about this dv by dt. So we can write this where this d by dt is the material derivative, which can also be written like this. Okay, all right, thank you for attending the lecture.